And today I'll be presenting my Lab 3 report. This lab focuses on the understanding of gravitational interactions in a two-body system, and later, in a more complex system, where orbital motion becomes far less predictable. Now, the purpose of the first part of the lab was to observe a star orbiting a black hole and determine the net force acting on the star. In the second part of the lab, the scenario shifts. We enter a spaceship within that same system, and our task is to try and achieve a figure-8 orbit around both a moon and a planet. We use two main physics ideas and principles throughout both parts. Firstly, the momentum principle, which states that the change in momentum over time equals the net force. Second, Newton's law of gravitation, which allows us to calculate gravitational forces based on mass and distance. Now, in the first experience, we define our system as a star, with the black hole being the surrounding object providing the gravitational pull. We go on to set the initial conditions for this simulation, calculating the net force on the star, and using that information to estimate the black hole's mass. Since the orbit is controlled by both mass and distance, observing how the star moves lets us work backwards to determine those properties. Now what really matters is, what does this mean? This means that the mass of the objects and the separation between them can determine the net gravitational force on an object. Meanwhile, changes in velocity tell us how momentum is changing. Even when our numbers differ, step by step, they represent the same physical ideas and lead to the same conclusion. What I learned here is that motion can reveal hidden information, like the mass of something we cannot directly measure, regardless of what we're given in the beginning. We can use surrounding factors to go ahead and calculate our desired number. Now, the second experiment introduces a far more complicated system. The spaceship and planet are considered the system, while the black hole, planet, and spaceship all also exert gravitational influences. We calculate the forces acting on the spaceship so that we can predict its motion. We then use the update formulas to simulate how the orbit has changed over time. Through trial and error, we're able to find a velocity that creates a stable figure-8 orbit around the planet and around the moon. This shows how sensitive orbits can be to even small changes in velocity or direction. Now, what if? What could have happened? We also have to consider questions like whether the spaceship could orbit the black hole instead. Now, the answer depends on the initial velocity and distance. If it starts too fast or too close, gravity may pull the ship into the black hole or launch it out of the system entirely. It's a very tender process that can be affected by the smallest changes. Now, real-world factors like other gravitational bodies or external forces could disrupt this orbit, which makes space navigation very complex. Now, what are some possible errors? There are a few things that could affect the accuracy of our results. For example, rounding or numerical precision from the simulation software has led to some issues with some of the first experiment stuff. And running the simulation for too short of a time can lead to inaccurate numbers. Also, assuming that there's no external forces beyond gravity is what's being made, is what's happening within this code, which is simply not the case in real life. These are limitations that we have to be aware of anytime we rely on modeling instead of actual direct measurement. Now, what can we conclude from this? Overall, we successfully estimated mass based on orbital motion, and we determined that the required velocity of a spaceship to achieve a figure-8 path around the moon and planet. This lab helps reinforce ideas that orbital motion is predictable. Regardless if we are given every single factor in it, we can use the pieces and measurements that we are given to try and solve for the ones that we're not. This is only capable, though, whenever we understand gravitational relationships involved. It also shows how physics allows us to solve for things that we cannot directly observe, and which is a key skill for studying space.